Okay, so welcome to lecture 33. While I figure things out up here first. This is going to be on purposeful design. And so what does that mean? That means that basically it's going to be about what's necessary for you to do your lab number 6, provided we can get there on time. But first, a few announcements. So first, your homework 10 is online. You know that. It's going to be due this coming Friday. It's been online for a while. Lab number 6 is online, and I want to go through that just a little bit. Hopefully you've taken a look at it already. And finally, your graded midterm 2 is going to come back today, provided Kieran shows up, because he's got him right now, and I don't see him here yet. But he should show up. I do have the solutions for the midterm, which I'll start passing around a little deeper into the class to make sure everyone is here to get them. Let's see. So that's basically all the announcements there. Any questions about anything? Okay. I guess I understand that PG&E may have another of these power shutdown things, so we'll see what happens. And if that happens, you know what's going to happen. I'm going to record something. I'm going to put it online on the Wednesday, and there's Kieran, right? So you are going to get your exams back today, but sometime later on in the class. All right, so let's start by taking a look at that lab number 6. Let's go on here. Let me bring lab 6 up. Okay, so this is your lab 6. So it's a lot like your lab 5, which is a design problem, except this one is going to be a lot harder. But hopefully it doesn't feel a lot harder for you because you'll have learned, how to put this together. So this is a multi-transistor circuit. That means that we've got, instead of just one transistor hooked up in a common emitter configuration, you choose the configuration. And you're going to be allowed 4 transistors to be able to meet these specs here. So if you look at these specs, you can see there's already some things that are a lot more difficult than what you were doing before. So the gain now has to be greater than 4,500. You can't do that with a single transistor and get good bandwidth performance. Your lower corner frequency is going to be 100 hertz. Your upper corner frequency is going to be 10 kilohertz. So actually, I could have done this differently and sort of required an upper corner frequency of 500 kilohertz. But instead of that, what we're going to do is do something more like actual audio design, where you would use a filter to try to cut off some of those really high frequencies there that don't sound very good. And so that's what you're going to be doing. You have to add a capacitor somewhere to get that 10 kilohertz corner frequency. And you need to add that capacitance in such a way that you use the least amount of capacitance possible. And so why do you want to do that? Because you want to make your design the least expensive. So you want to use as small a capacitance as you can use. Input impedance greater than 100 kilo ohms. Output impedance less than 20 ohms. So those are very much like what you need for a voltage amplifier. Undistorted output voltage swing greater than 3 volts peak to peak. All specs met while you have an oscilloscope probe and a load resistor of 100 ohms. Like I said, no more than 4 transistors total, either of NPN or PNP type. Minimize external capacitance, like I said. That includes your coupling and bypass capacitance. You want that lower cutoff frequency to be 100 hertz, but you want to achieve that with a small amount of capacitance as you can. Reasonable bias stability, and so you know those equations for stability. Use the standard values that you have in the lab, and your source resistance is going to be 4 kilo ohms, and your supply voltage is going to be 12 volts. 12 volts and 0 volts. Okay? You can read the rest of this stuff here, and you should read the rest of this stuff to see exactly what you need to do. So there's hints on how to test the amplifier and that sort of thing throughout this. I'll let you go ahead and read that. There's remarks here on more stuff. You'll have to use an attenuator circuit in order to actually determine your gain, because the signal generators we have cannot put out a small enough signal. Now your gain of 4,500 is going to gain that up so big that you need a really small signal to keep the output less than 3 volts peak to peak. And so you need some kind of attenuator circuit to do that. So here's an example attenuator circuit for the case where you have the signal generator in the 50 ohm output mode. I understand there's a high Z mode that you can use too, which will change this a bit. So you think about how that will change that if you decide to use that. And so this lab will be like the lab number 5 in that you'll have to do a hand analysis, you'll have to do a SPICE simulation, and you'll have to actually build the circuit on your breadboard and prove that it works, measuring it using the equipment you have in the lab. And so that's all explained in all of this here. I won't go through this in great detail because you should read this here. We say a few things about what you need to do for hand design, transistor measurement, SPICE simulation. And then the big part of this is going to be the report. Okay, so we're sort of explaining to you what your report should contain, although it's sort of up to you how you organize it. But like lab number 5, remember what is seen by the person grading this is that report. They don't see necessarily what you did in the lab and all the struggles you had in the lab or so. So make sure that all your stuff that you want to put in the report is captured in the report. Make the report look nice. Okay? That's just the way the world works. And so in your report, make sure you have a design strategy and discussion. So that's something where you're talking about, okay, I tried this first. The bandwidth turned out to be too low, or whatever happened there. And so I made this adjustment to do that. And this adjustment was guided by this equation. So that's sort of how that discussion should look like. Your hand design, I guess those are sort of related there. Computer and SPICE simulations, that's obvious. Experimental results, that's kind of obvious. And a summary, including a table. So you want this table to be something where you're comparing your hand analysis with what your SPICE said, with what your measurement said, something like that. I guess that's all I'm going to say for now. I mean, there's plenty of time later on to discuss this more. But this is your lab number 6. It was actually up on Friday. It's not going to be due until the last day of the RRR week, which is a Friday, and that's December 13th. And so you got about a month to do this, which I think is plenty of time to do it. And in this lecture today, we'll talk about some of the things you need to know, at least in order to put the transistors together in the right order to get this performance. Okay? So that's your lab number 6. Yes?
I have a question that will the lab 5 report be graded soon in 1 week so we can know the feedback of it?
Yeah, it'd be great if that were the case. So let's look back to Kieran, who happens to be in the back of the room here, with a big smile now. He's asking what was the question. So the question is, will Lab 5 be graded in say 1 or 2 weeks so that they know how they did on that before they turn in Lab 6?
Yeah, I think you should get the grade a week or 2 left before your Lab 6 report is due.
Okay, so he's saying a week or 2 left before your Lab 6, you'll have them done. So you can hold him to that now, right? Him and the rest of the team. He's not grading them all, right? So Ali and Jeff are also grading as well. Any other questions about this lab? Okay, remember this is a big part of this class. It's a very large percentage. You can see right on the first sheet, do well on this lab. And this lab is not easy. Okay, so try to get it done, as much of it done early as possible. Okay, and so, yeah, you don't want to be, this is the part in this class where you may be pulling all-nighters if you have not done this lab before the last week. Okay, and that's happened in the past. I can see the poor individuals doing that. I know that you're all struggling with other projects and other courses, so this one I don't think is that bad, but get it done early, because this is a type of thing where you could hook something up and something that you don't understand can go. That's part of the education, to hook it up and to try to debug the thing. But that could take some time. And the gain here is so high that it's possible that on your breadboard you can get things like oscillations that we'll talk about, which means you've hooked everything up nicely and it should work, but instead of working, what's happening is it's just oscillating with some huge sine wave, even though you don't put an input signal in. And that way you're basically creating an oscillator, which is a very important circuit. My research group does oscillators, right? We're researching oscillators, but you don't want an oscillator in this case, right? You'll learn that it's easy to make an oscillator when you don't want it, and it's hard to make an oscillator when you want it. It's kind of what you'll learn in this case if your gain is very large in this. All right? Okay, so that's lab number 6. And so now let's go back to lecture material. I guess maybe 3/4 of the way in class we'll hand out the exams. So let me do this first. Okay, so last time we were doing mid-band MOS inspection analysis, and I basically went through deriving all the equations for inspection analysis for MOS, and hopefully you watched that video. I've noticed that the people are falling behind on the videos. I mean, all the videos up to the point where the cutoff for the midterm are watched. Okay, but now you got to start getting into it and catch up to the videos at this point. But this was sort of the last thing that I showed. This is the inspection analysis formula quote sheet for MOS, at least for midband here. And I think the main takeaway, if you didn't see the lecture from last time, is all we did to generate these was take the bipolar equations and let beta go to infinity. That's it. Okay, so these are the same equations as the bipolar equations, except we let beta go to infinity. And then we spent some time last time talking about the fact that if you don't tie your bulk to your source, okay, you also need to add in the GMB. Okay, well, do you need to? Well, it depends on your transistor. If you have a long channel transistor like what we're playing with in this class, you don't even need to care about the GMB. In that case, everything just falls back to bipolar equations with beta going to infinity. Okay, but if you have a short channel device, like what you'll see, say, 140 or 240B, if you ever take that, then you have to take GMB into account because it becomes significant. And so that's why I'm showing you this GMB. In this class, if you don't show that GMB, and it's just a calculation thing where you need to just get in the ballpark, that's okay. If we ask you for an explicit formula, though, and we don't ask you for a calculation, then you got to get the formula complete, even with the stuff that you normally ignore, and then you want to put that GMB in there. Okay, but for now, these are those inspection analysis equations. They're the same as the bipolar ones, okay, with beta going to infinity. So you don't even have to memorize this. You just memorize the bipolar ones, and then when you need to do MOS, you just let beta go to infinity for those equations, okay? And so we did a midband analysis for this last time. I'm not going to go through that again because you can watch that lecture, but what we didn't do was the high-frequency analysis. So at least I'm going to do the high-frequency analysis for you. Oops. Undo that. So let's go through the high frequency analysis for this so you can get some semblance of how we do these MOS things. So I'm assuming that we've already reduced this to the small signal model, which we have here. Okay, I showed the large signal thing, or the large signal circuit last time, but I even showed that in kind of a halfway method because I didn't show the full biasing of that. We'll talk about full biasing of MOS a little bit later on here. But right now, suppose this MOS 2-transistor circuit has been biased, and now we're interested in the high-frequency analysis. We're going to do our high-frequency inspection analysis here, which means that I need to get this in our small signal circuit. You can see I've done that. I've got a source there. I've got what used to be VDD going to ground. All the sources are shorted out. Okay, and I want to do high-frequency analysis, so what I want to do is put in my capacitors first. So this is MOS. Capacitors will be a little bit different, but not that different. Because I still have a capacitance going from, in this case, my gate to my drain. And that I'm going to call CGD. And I'll call that CGD1 because that's for transistor 1. I still have a capacitor going from gate to source in this case. So that's a CGS1. And we didn't talk in great detail about these other capacitors, but remember the source and drain are junctions. And so associated with any junction is a capacitor. And so I can add some junction capacitors, which I'm going to do here. I'm doing this mainly because if you get to take 140, they will talk about these capacitors as well. So the junction capacitor from the source junction to the bulk, remember that's a depletion region capacitance, so I'll call that CSB1. And then I've got another depletion region capacitance here that's going from the drain to the bulk, so I'll call that CDB1. Okay, same capacitors for transistor M2. So I have a CGD2. I will have a CDB2. I will have a CGS2. And I will have a CSB2. Okay, so those are all the capacitors that I'm going to have to worry about for my high frequency analysis. And so I want to do this using the Miller transform. So I'm going to take any transistor that is in a feedback position and turn it into Miller capacitors, because I don't want to memorize that driving point resistance for CGD, which is going to be the same equation as for C mu for a bipolar transistor. Okay, so all these equations, even for the time constant analysis, are the same as those for bipolar, except you let beta go to infinity. Okay, and so before even doing all this, let's see if we can eliminate any capacitors. Are there any capacitors in this circuit that you would just eliminate outright? Yeah, well, you said SB1? Yeah, good. So SB1 you eliminate because it's between two grounds, right? Gone. Any others? Yeah, CDB2, also between two grounds. So if it's got ground on both terminals, it's not there. Okay? And so those are all the capacitors I can eliminate. The other ones I should take into account. And so the first thing I'm going to do is get rid of this CGD1 and turn that into two Miller capacitors. And so my first Miller capacitor, CM1 I'll call, that's going to be equal to that capacitance value, CGD1, times 1 minus the gain of that first circuit. But the gain of that first circuit is what? We determined that last time. Here's our chance to determine it again. It's going to be the GM of transistor M1. So we minus the GM of transistor M1 times all the resistance we see at the drain. Just like bipolar, minus GM times all the resistance we see at the collector. Okay? Except in this case, just the drain. So minus GM minus GM is plus GM. So I have a plus GM1 there. And then all this resistance I see out there, I see an R0 going down M1, but I'm going to assume that's big. I see a resistance going forward into M2. That's infinity because it's a MOS transistor. And so the only resistor I'm going to take into account is this RD1. And that's my Miller capacitance hanging off the input node of M1, which I'm called node 1 there. Okay? But remember, I also have another Miller capacitance that's hanging off of this node, which I can call CM2. And what's that going to be equal to? That's 1 minus 1 over the gain. What's 1 over the gain? It's pretty much 0 if the gain is big, right? So it's just going to be this capacitor, CGD1. And so that's all that's hanging off of the drain node there. And so now with all of this, I could start doing my analysis. And so I'm going to go node by node. Let me go blue. Let's get my time constant at node 1. And so that's going to be equal to all the capacitance I have at node 1, which is going to be equal to that CGS1 plus the Miller capacitance I just wrote down. So that's CGD1 times 1 plus GM1 times RD1. And that's now going to be multiplied by all the resistance that I see going to ground from this node here. And what is that resistance going to be? Well, I see infinity going into M1. I see RS going into VS, which is ground there. So the resistance is just RS. Okay? And so I can move on to my second node. So the time constant at node 2, that's going to be all the capacitance there, which I can see is CGD1 from the Miller effect, plus CDB1, plus the capacitance I see looking towards M2, which is not going to be CGS2, because notice CGS2 is in that feedback position. So I don't really want to include that as shunt capacitance. It's not in shunt. But I do see a CGD2 going up to ground. Okay, so those are all my capacitors. I'm going to multiply that by the resistance I see at this node. Resistance I see at that node is R0 of 1 in parallel with RD of 1, but R0 of 1 is big, so I'm going to ignore that. Okay, and looking this way into the gate of M2, again, that's infinite. So I'm going to ignore that resistance. Okay? And so tau 3, I'm now looking for all the capacitance at node 3, which is this node here. Let me write. So that's at my output node 3. And so all that capacitance is just going to be one capacitor. That's just CSB2. And that then is going to be multiplied by the resistance I see looking up into the source of M2 in parallel with the resistance I see looking down, which is just RS2. So looking up into the source of M2, remember, is a 1 over GM of 2. But if I want to be accurate, I could say plus GMB of 2 there. I'll put that in parallel then with RS2. Okay? And so that now is that time constant. Finally, this time constant associated with CGS2. So this is going to be the tau GS2. This is going to be equal to, of course, that CGS2 capacitance itself. And then to determine what that inspection analysis equation needs to be, right? That's in feedback. I need to know that equation. That's the same capacitor as CμU in the bipolar case. So remember, in bipolar, the driving point resistance for CμU was this, R pi in parallel with RB plus RE over 1 plus GMRE. R pi is what for MOS? It's infinite, right? It's beta over GM. Beta goes to infinity, so it's infinite. So I really just have this equation here. Okay, and so if I just have that equation, then I can return to this, and I can just write that driving point resistance as just whatever resistance I see, whatever resistance I see looking this way, which is RD1, plus the resistance I see hanging off of the source, which is RS2, divided by 1 plus GM of 2 times RS2. Whoops. But that has to be in parallel then. Oh no, that's just it. Wait, let me be more accurate here since I did that above. That's GM2 plus GMB2 times the RS2. I'm trying to put that line down the S to make it capital. Somewhat like that. Okay? And so that now is the time constant associated with tau GS2. Now, if you went ahead and derived this, you would see that in actuality, you know, in actually you need to add to this numerator a GM2 times RD1, sorry, GMB2 times RD1 times RS2. But GMB is small, so in many cases we just ignore this. But there really is that term if you wanted to go through and actually derive this equation. That term does exist there. But we're ignoring that for now. And so one question that I want to ask, well, before doing that, let me just write the whole solution to this. So the final solution to the high frequency omega h is just going to be 1 over all of these time constants. So tau 1 plus tau 2 plus tau 3 plus this tau GS2. So that ends up being the total solution to this. But now, before even calculating any of those things, you want to look at this and say, okay, which ones are ones that I really want to calculate? Because if I want to save my time, I can eliminate one of them, or more than one if you so choose. But if you were to eliminate one, which would you eliminate to calculate here? None of them? You calculate them all? That's fair. If you have enough time, you can do that. Or if you're not lazy. But if you're lazy like me, okay, CGS1? Yeah, CGS2. Because this last stage here has a gain, not unity, but it's close to unity. And if I have a gain of unity, that means I have no voltage variation, very little voltage variation on CGS2. So what I might do is ignore. So for CGS2, ignore, since the signal across CGS2 is tiny. Okay, since the gain across it is about equal to 1, right? So that same principle I would use that we've been doing with bipolar. I would just ignore that thing. Okay? So any questions about this high frequency analysis that I just did, or MOS analyses in general? Okay, so let's move on to what I call purposeful design. Okay. And so to do purposeful design, what you want to do is know the popular amplifier configurations. And so we talked about the common emitter amplifier, but it turns out that that common emitter amplifier is a building block for larger amplifiers. So you understand the common emitter amplifier very well, but we talked about this before. You can get other types of amplifiers like common collector or emitter follower by just degenerating the emitter and taking the output from the emitter. Okay, that will give you what's called an emitter follower. You can also get what's called the common base amplifier by just driving it at the emitter and taking the output at the collector and setting up your bypass capacitors such that the base gets grounded. So this is an example of the bias circuit for that. It will give you common base. You could also get a common emitter amplifier but just degenerate it. So you still be taking your gain from the base to the collector, but you put an emitter degenerating resistor on the emitter. And so this would be the actual DC biasing circuit for that. So here, now we looked at these small signal circuits. I'm now showing you the DC biasing circuits next to these things. And so why am I showing you these? I'm showing you these because these are the basic amplifier configurations that people use to create bigger and bigger circuits. If you know each of these configurations, you can recognize them in bigger circuits, and then suddenly a big circuit just becomes your ability to analyze a big circuit becomes your ability to just identify these blocks. Okay? That's how people look at big circuits and immediately know what they're doing. Okay, so let's go ahead and look at each of these different configurations one at a time. Okay, and so this is how you would actually design a multi-stage amplifier. Okay, so what I've got here are the things that we care about with amplifiers, right? Input resistance, output resistance, gain, high frequency response. I don't have low frequency because you could pretty much design that any way you want for any configuration. But certain amplifiers are good at gain. Certain amplifiers are good at input resistance. Certain amplifiers configurations are good for output resistance. But none of them are good for all of them. So if you want something that's good for all of them, which is kind of what your lab number 6 is demanding, you can't do it with just one transistor. You have to put many transistors together and create a bigger circuit of that. So let's go through and analyze what we had before. So right now we've got this emitter follower amplifier here. Okay, so that's common collector. And so that's this right here. And so with common collector, let's take a look at the different properties of common collector. So if I take a look at the input resistance for this, so say I was looking at this and say I just was looking in this direction here, I mean I probably ought to really, what I'm really interested in is that RI, but say the biasing is going to be big. The RBs are usually pretty big, right? But what's this resistor looking into the base of a common collector amplifier here? So it's just going to be equal to 1 over GM of the transistor plus whatever is hanging off of the emitter, and all of that times beta plus 1. Okay? If that's what that's equal to, this is very large. Right? And so for the common collector amplifier, I'm going to go ahead and say this is large. The input resistance. That's nice and large, and so I'll put a check mark next to that. Check mark means good. Okay, so that's large, and for a voltage amplifier, like we said, they like to have a large input resistance. Okay, I can go back and look at this again and look at my output resistance, and so my output resistance is looking up into the emitter of this transistor. Remember, that's equal to a 1 over GM, right? So if I'm looking at that, then this is basically a 1 over GM. If I want to be more complete, then that's also plus RS parallel with RB in this case divided by beta plus 1, which is going to be also very small. So this whole thing is going to be small. And so the output resistance of the common collector is small, and I like that, because that's what a voltage amplifier's output resistance should be. Okay? How about the gain of this thing? So this is an emitter follower. We looked at that gain. It's only about equal to 1. Okay? And so the gain is small. If I'm interested in voltage amplification, I don't like that. So I'm going to put an X right there. Right? So the common collector so far, it looks like a great voltage amplifier in terms of input resistance and output resistance, but in terms of gain, it's awful. Okay? Now, in terms of frequency response, what can we say about this thing here? Well, the main capacitor is this capacitor between the base and the emitter. And remember, I have a gain of 1 across that, so that capacitor gets knocked out. I don't have any gain really from here to up here. Very small gain there. So the C mu is not multiplied by a Miller multiplication. And so in the end, I expect to have a very large frequency response for this. And so that's good. So the common collector, it gets 3 of the 4 categories right, but one of the categories it does awful at. The gain is just 1. Okay? And so let's take a look at some of these other configurations here. So the next one that I have here is our common base amplifier. Okay, let's do the same kind of thing with this. So if I look at my common base, I've got that input resistance there. What is that input resistance? If I'm looking into the emitter of this transistor. You guys have forgotten your inspection analysis? R naught. No, it's not. You're looking into the emitter. R naught is looking into the collector. Right, that'd be correct if we're looking at the correct collector. But we're looking up the emitter now. What do we see up the emitter?
R little e?
Yeah, that's right. R little e or 1 over GM. Which is a very small resistor. It's about 25 ohms or so. So that I can identify as small. And so right away for my common emitter circuit, common base circuit here, the input resistance is small. That's not good for a voltage amplifier, so I'm going to put an X there. Okay. Continuing on this, I can look at my output resistance. So what's the output resistance of this thing? And so just by inspection, I will see, yes, an R naught there. I'll actually see even more than that. And so it's going to be R naught times the rest of that stuff that comes with R naught. But that's going to be in parallel basically with this RC here. Well, I won't include the RL there. Right? And so that is large. RC is relatively large. It's big for an output resistance. And for, again, a voltage amplifier, we don't like large output resistance, so that's no good either. So common base so far is striking out in 2 of the categories that we care about. Now in terms of gain across this thing, remember what that gain is now. It's equal to about GM times my output resistance, which is RC in this case. That's pretty large. Okay, so that gain I'm going to say is large. And I like that. I'm going to put a check mark there. Okay, and then finally, the frequency response of this thing. What can we say about frequency response? Well, we have to look at the capacitors. And so I have a C pi right here. I have a C mu right here. None of them are in a gain multiplication position, right? None of them are in feedback where we're actually multiplying that gain. And so because of that, they remain small capacitors, which means I have a very good frequency response for this. My frequency response is going to be large, so I'll say large. And I like that. So common base hits on two of the quantities, but misses on 2 of the quantities. Okay, so we keep marching on. So the next circuit we have here is the common emitter with degeneration. And so we again have this situation where we have an emitter degeneration there. And so again, this input resistance is going to go as 1 over GM plus the RE1 times beta plus 1. That's going to be large. And so if that's large, I'm going to say large here for my input resistance. That's good. Okay, my output resistance in this case, it is that RC again, right? Which from output resistance standpoints is large. I'd like it to be 50 ohms or less. But RC, you know, is a kilo ohms, some number of kilo ohms there. And so that's large. And so in this case, I don't like that. The gain of this common emitter with degeneration. So it's got degeneration, and by definition, that means I've lowered my gain by that RE resistance. So remember, the gain in this case now is going to be that same GM times RC. Okay, but remember, I'm lowering that now by 1 plus GM times RE1. Okay? And so if I'm going to do that, this is going to be smaller than the gain of a common emitter amplifier, but it's not as small as the common collector. So I'm going to say this is medium. Okay, and so I'm going to put a check mark with a hash on it, which says it's not quite good, it's not quite bad, it's medium gain that I'm getting out of this thing. And then finally, as far as frequency response is concerned, because I have medium gain, I am amplifying the C mu through the Miller effect there, but it's not a big gain, so it's not amplified that big. And so I would say that it has medium frequency. So I'll do that, check mark with a hash mark there. Okay? And I guess to start with, I should have put my ideal stuff. I said this, but let me fill this column. Ideally, I would have an input resistance of infinity. I'd have an output resistance of 0. I'd have a gain of infinity, and then I have a frequency response, an upper cutoff frequency of infinity. Okay? And so that's what tells me what's good and what's bad there. Okay, and finally, the common emitter amplifier, which we know so well, what would you say about its gain, or about its input resistance? Common emitter amplifier. The one you just designed for lab number 5. Good? Yep, medium, I would say. Because it's not a gigantic input resistance. It's an R pi. So that's a medium. Okay, how about the output resistance?
Kind of large.
Yep, I would say large too. Because that's the RC. I don't like that. Doesn't match that 0 there. How about the gain?
Large.
Yep, it's got nice gain. So let's put large there. And how about the frequency response?
Large.
Why would you say large?
I got pretty high upper cutoff.
What did you get?
1.2 megahertz.
1.2 megahertz? Okay, I guess that's okay, but it's not generally large. You get even larger if you put that same transistor in an emitter follower. So the problem is that in the common emitter you have a lot of gain. So you take C mu with the Miller effect, you're multiplying it by that gain, and that's killing your frequency response. So it actually has a small, compared to the other configurations, frequency response. So there it is. None of them do what we want them to do. None of them are perfect. And so to get better performance, we need to combine them together. And so let's do that now. And so what you'll be doing in your lab is to cascade these stages. So each of these is an amplifier in itself, but if you cascade them as stages, you can get the best of all worlds here. And so for a good voltage amplifier, okay, what would I do? I want a high input resistance, and I want this thing that gives me the high input resistance to have a low output resistance so it can drive a next stage that might give me my gain. And so a nice thing to do is to use a common collector amplifier right up front. So maybe I would do this, and I'll put CC for common collector there. So my input voltage would be there. And if I did that, then looking into this, I would see a large input resistance. Perfect for what I want. Okay, the problem with this is my gain would only be 1 times. Okay, so in order to solve that problem, I will drive another amplifier stage designed to give me a lot of gain, and maybe I'll choose a common emitter amplifier because that gives me a lot of gain. And so the output resistance of this is small. So even if the input resistance of the common emitter amplifier is medium, that's okay. Because I'm driving a medium resistance with a very small output resistance, I'm not going to lose much signal through the voltage divider there, right? And so, right, the fact that I basically have this here, I have small here, I have medium there. If that's VI, well, let me not use VI. If that's VA, and that's VB, then VB over VA is about equal to 1, and I like that. Right? Otherwise, if it's much less than 1, then I'm losing gain in this. But right here, what's great is that CE gives me A sub V times gain there. Okay, but the problem with CE is, remember, its output resistance is large. And so if I'm trying to drive the next stage with this output resistance, I'm going to lose a lot of gain because of this same effect. Right? Instead of small here, I would have large there. So what I want to do is have the next stage have a very large input resistance, and I can do that again with my common collector. So I could then use a common collector stage here, which has a larger than that input resistance, okay, which then allows me to drive this voltage here because the output resistance of common collector is small. Okay, and so the output resistance of this whole thing would be the output resistance of that common collector, which would then be small. Right? So here we're looking at this. R naught equals 0, or something very small there. And you have some Ri. In this case, the gain is about equal to 1. Okay? So that's how we cascade these stages in order to get whatever gain and frequency response we want. We're doing that is because we know about the common base, common collector, common emitter with degeneration stages, and we're just going to use different combinations of those stages to get what we want out of our circuit there. Okay, so with that, I guess what I'm going to do is stop here and we'll take a look at your exam stuff. So let me pass around the solutions to the exam first. So the last person, please bring me back the rest because I'll put those in the front of my office. I guess we'll wait till everyone gets a copy of that. Okay, so here are those solutions right here. So problem 1 was basically just short answer there. Hopefully you can get these very quickly, but some of them are thinkers. I guess the last one caused some people problems because people may have thought that there wasn't enough information given, but there was, because a lot of the other stuff you could ignore. The only thing that was important was the Miller effect capacitance. And so if you recognize that you can ignore everything else, then you can get an approximate upper cutoff frequency, which is what it was asking for, just something approximate there. Okay, the problem number 2, I guess this came down to whether you knew what to do with this current source. You know, that you had to open circuit that for the small signal analysis. It also came down to whether you tried to inspect, analyze this R1, C1 combination here, which you actually could do if you knew what you were doing. The solutions actually does it in several different ways. Well, the solution does it in the brute force method, right? Assuming that if you ran into that, it's a configuration you hadn't seen before. So the best thing to do is just replace the C1 with the voltage source here and measure the current across that to get that driving point resistance. The other thing you could have recognized is that you could have just used the driving point resistance equation for C mu in this case, and replace C mu by the series combination of R1 and C mu, and then just solve then for the resistance across the original C mu, or the C1, sorry. So you could have done that by inspection too. And so you may have noticed someone finished really early. Probably that's what happened with that case, right? You could have inspected that. But if you didn't, you would have gone through all of this math here to get that answer. then in the end you would get that final frequency there. So I think the rest of the solutions are pretty self-explanatory in front of you. I think at this point, let's now pass out the exams. So Kieran, if you want to do that. You don't want to call names and have people come up. There's enough people in the class to do that. Or you can, yeah. That might be easiest, right? Because then you could just...
Yeah, I'll call names. Sonny? So, average is 80.
Yeah, give the average and the mean, too.
Okay, so it was out of 141 points. Didn't change. Average was 83.6, so about 60%. Standard deviation was pretty large, so it's 27. And then the median was 85. Shengbo, Iris, B1, Siobhan, Amanda, Jackson, Jonathan, Kim, Ian, Anvisha, Jacob, C1, Tang, and then Amanda. I think that's everyone in here.
All right, so can you repeat that again? What was the average?
Yeah,
Was...
now that you have it in front of you, the still out of 141 average was 83.6. Standard deviation was 27.1, and then the median was 85.
Okay. So that means it's a very good exam again, right? Because the average and the median are very close. But anyway, that's pretty good actually for this exam here. That 85 is pretty good. So you should be happy with what you've done, I suppose. Look at the solutions to see what the differences might be between what you did and the solutions. And remember, this is only just part of your grade. I don't have the Z's yet, so next meeting I'll come with Z scores, and that hopefully will include all of your homework grades and lab grades up to the latest ones, at least that have been graded. Okay? Any questions about this?
Just a comment overall, I think the most like widespread struggles were with the biasing actually of number 2. You know, there were people that struggled with the upper corner, lower corner frequencies and vice versa, but almost everyone kind of had some issue with the biasing. So make sure you kind of understand what was going on there. Feel free to come talk to me if you have questions about the solutions or the grading. But yeah.
Okay. Anyone want to talk about biasing?
I think the current source was definitely tricky.
Oh, that part, yeah.
I mean,
okay.
Yeah, there were some confusion. And, yeah.
All right, so I guess that's it for today. I think I'll see you on Wednesday. But if not, I'll record that lecture. If PG&E shuts down power is what I mean.